Everyone, I am Saurabh Sohni from Amazon Machine Learning team in Bangalore. I welcome you all to the third session of GHCI's 2015. I would like to take this opportunity and introduce some problems that we are solving related to machine learning in Amazon. And I hope you will all get excited with the work that we are doing. And you guys can come to our booths for more detailed discussions if you want. So. In this particular session, I'll be talking mostly about. This doesn't work? Okay. Can you click next? Yes. So there are multiple verticals which are related to ML and a lot of exciting problems to solve there. But next 5 minutes, I'll spend time on the catalog. So what do we have here? Amazon at its core is all about selling products. And there are sellers who sell the products. There are customers who come to the website to buy the products. So for each product, we have like a lot of information like title, description, bullet points. And the top red dot that you see, square, is the hierarchy in which the products are distributed across the catalog, right? So the problem here is, given a product description from a seller, map to appropriate node in the product taxonomy. So this product taxonomy is defined for proper navigation for a customer, right? You could search the products directly in the search query box, or you could navigate starting from a root node to, let's say, electronics, to cameras, to Canons, and to accessories and all that. So here the problem is to classify this product into the correct location in that hierarchy. So there are, next slide. Somehow this is not working. Can you click next? Yeah. So there are a lot of challenges that we had that I want to highlight here. I won't go into the details, but scale obviously is a big challenge because we are working here with hundreds of millions of products and thousands of classes in the taxonomy. And the class definitions are fuzzy, right? There is no proper taxonomy defined as such. It evolves over how things are bought by customer, what is the behavior they are exhibiting on the website. So this taxonomy is kind of fuzzy. There are a lot of cases where the nodes and the bottom are overlapping, right? A book on photography can be classified under photography, accessories, and books, or it can also go from books to photography and arts and photography books. So these kinds of nodes at the bottom level are overlapping. So we would. And in fact, a product can also belong to multiple nodes, right? So there the problem of multi-class versus multi-label exists. And the problem is also about, given a new product from a seller, how do we put it into the correct hierarchy? So lot of the times the data is incomplete. Sellers don't know what exactly to fill in. So these are the challenges that exist. And next slide, please. So the other problem that I want to highlight is about product matching. That is also a very key problem considering the scale that we work at. So there are millions of products, and millions of products come in every month or every year. So we don't just want to put them in the catalog, right? We want to assign them to the right place and to match them to the products which already exist in Amazon in order to remove the duplicates, right? Because as clean the catalog is, the better will be our search and customer experience. So here the problem is to, given a product information like title, description, price, we want to find duplicate product listings in Amazon catalog. So for example, you might want to club all three into one product which talks about whatever this juicer or mixer is, and the color or the capacity can be its variants, right? So that is a problem. Next slide. So the kind of challenges that exist here is, again, the scale, because the catalog has hundreds of millions of products. And we want very high precision here, right? So if we can trade off recall, like if there could exist two products which are independent but same, but there cannot be two products which are clubbed together and they are not same, right? And to some extent, there also exists a relation with the domain adaptation part, like for example, in case of iPhones, you cannot club iPhone 5 and iPhone 6 together, right? Because they are two different products. Whereas if you consider, let's say, SanDisk pen drive, you can say a 4 GB or 8 GB are variants of the same product. So it's very subjective, and that is where these diverse formats and variations come in. So that is where I'll end, and we have a booth there, and we can have more discussions if you are interested and excited about the problems that we are solving. Thanks a lot. And for the next session, I'll like to call research scientists from Xerox to discuss more about domain adaptation. Thank you.
um, principles, applications, and theory. So before I start, I'll just introduce myself. I am Himanshu. I am a research scientist at Xerox, and this talk will be given along with my colleague Manjira, who is also working with me on this problem of domain adaptation. But before starting, can I just ask you, how many of you have heard of transfer learning or domain adaptation techniques, or have ever worked on those? Okay, great. Please, next slide. Okay, so the content of this slide would be, we'll start. Okay, so I'll just give you a brief introduction about domain adaptation. What are the different problem settings that can arrive in domain adaptation, and possible techniques, and I'll give you some real life examples on which currently we are working on, and we see how these techniques, transfer learning and domain adaptation techniques, can be very useful in real life settings, and what are the main benefits that it has that are not available in traditional machine learning or other supervised learning algorithms, right? So let me start with a real life problem which talks about how, just to give you an overview, how machine learning algorithms work. So let's say I have a simple problem of whether I should process a loan for an applicant or not, right? So what kind of features will I see in that application? What is his age, marital status, annual salary, outstanding debts, or credit rating, right? So these can be some of my features that if I am a human, I'll see to make a decision whether I should process his loan application or not, right? So the task of machine learning, to put simply, is to write a program which can process these features and give me a decision whether I should process his loan application or not. Can you please put the next slide? Next slide. Okay, I can change it now. Okay, so the features can be binary or discrete. For example, here on the bottom side, I saw age, has job, own house, credit rating. So these may have different values, and my task is to learn a classification model. It can be, so these kinds of approaches are called supervised models, where I have a previous labeled data where someone has manually annotated whether, for, let's say I have 100 applications, and for all those 100 applications I have attributes which has age, has job, own house, or credit rating, and someone gave me a manual annotation whether I should process a loan application for this fellow or not, right? Let's say I have some past examples, and on those past examples I train a model which is basically a classifier which takes all these inputs and then give me a classification, yes or no, right? So what a machine learning algorithm works on is a past human coded examples, and then try to see or predict the same thing for an unseen example when I don't have that human annotation. Please, can you put the next slide? Yeah, so the data here is a set of records that I have already processed. I use this as past knowledge and trained a classification model. And the task is to predict whether I should process loan application for further unseen instances, which are again given to me in the problem or the attribute form, right? But let's say this was a problem I needed past examples or experience in terms of human annotation to learn a machine learning model, which is called a supervised model, and which performs pretty well when the task is same, right? For example, but now I have a different problem. Instead of a loan application, I want to see whether I should issue him an insurance or not, right? So the features that I'm trying to process in this problem more or less remains the same, right? What is his credit history? Does he have a job and all that stuff? Based on those attributes only, I'll take my decision whether I should now issue him an insurance plan or not, right? But for a machine learning algorithm or a program to understand that, it does not know that these features or the past knowledge that I have already gained while learning a classification model for loan application can be reused for doing the new task, which was an insurance plan, right? So how traditional machine learning algorithm works for a slightly related problem as so, how we would like to build a classifier is like I would again have some 100 instances or 100 users. I will have users to annotate whether given these was the attributes, whether I should have given him an insurance plan or not. And then I would have independently trained a new model which will just predict whether I should issue an insurance plan or not, right? So you understand the problem, like these two tasks are very related, like whether I should issue a loan or I should issue an insurance term plan. They work on same kind of attributes or are very related to each other. As a human, I can understand that whatever knowledge I learned while in the previous task, for example, loan application, can be reused. But how do I impart this knowledge to a machine learning algorithm so that he, sorry, yep. Yeah, no problem, please.
So, do you just do like a yes no out of this model, or do you also kind of give suggestions, or like you said, let's say the type of insurance, or what can be the loan pre-qualifier based on the data that you probably have all that data saved somewhere, right? So, in your kind of models, do you do those kind of analysis as well?
Yeah, definitely. So just to answer your question, so this is a toy example which I have taken, and it's a simple two-class classification problem, yes or no. But like you can do this transfer learning or domain adaptation things to more complex problems, whether it's a sequential labeling problem where you have to analyze the conversations, or it's a multi-class problem, or like wherever you can apply a machine learning algorithm, you can further extend those machine learning algorithms to reuse the previous knowledge so that they don't have to rely or learn every task independently, right? Please, next slide. Yeah, please, next one. I just covered. Yeah. So I'll go through this slide and I'll explain why do we need domain adaptation or transfer learning when we have different kinds of machine learning algorithms and what are the limitations of these machine learning algorithms. So just to highlight this point I previously mentioned, like machine learning algorithms don't assume that the new task that I will be learning may have some kind of relation with my previous knowledge, right? So you can intuitively visualize it as how humans learn. So we have an innate ability of reusing our previous knowledge, whatever we have learned in past, right? From childhood we are trained that way. For example, if you know how to play tennis, playing lawn tennis or something comes intuitively to you, right? If you know how to code in C++, then transforming to Java is very easy for you, like because you can use all your knowledge that you have learned in C++, you can use the same concepts and learn a new language in a much more efficient way. So that's the basic idea of transfer learning, how you can enable a computer program to transfer its knowledge which it has learned in a previous task to learn the new task in a more efficient way without requiring a lot of annotated data and without requiring the need to retrain models from scratch in all new domains, right? So it's just a cartoon here which displays these things. Can you just please press next? Yep. So like machine learning algorithms, if we try to see in real life settings, nowadays machine learning algorithms are used in all spheres, even in all spheres of life, right? And everything today is being think around machine learnings for automation or analytics, right? The main challenges is like you can do or process a large amount of data and gain a lot of insights in a more scalable manner rather than doing it manually or by other means, right? So that's why machine learning algorithms or automation by machine learning is a big area this day. But there are a lot of challenges as we discussed, right? Some of the challenges are, right, it requires, whenever you apply a machine learning algorithm to a new domain or to a new task, the data in a new task is always unlabeled, right? There's very few instances which may be labeled, right? And so how machine learning algorithms work in these problems, either you hire humans to annotate data for you so that you have sufficient label data on which a traditional model or machine learning model can be learned, and you can then process unseen data, right? But imagine there are lots of domains like healthcare, telecom, retail, and just doing a simple task on different domains may require a lot of time in terms of getting this annotated data, which is very expensive and costly. And it's not a feasible solution, right? Whenever you get a new task, you can't just start by, okay, let me get some label data and then train a model so that I can process further. You need to reuse your previous knowledge, right? How machine learning algorithms can reuse whatever they have learned from maybe other related domains. Please, next slide. Okay. So this is the traditional view of machine learning algorithm, right? Given a new task or a domain. So domain here can be, let's say a task in a specific domain. Let's say I'm talking about a sentiment categorization. So the task of sentiment categorization is to classify a piece of text as positive or negative. Let's consider it's a two-class problem. So let's say I want to do this for a telecom or a phone product, right? So I need to have a labeled or annotated data so that I can train a supervised model. So I call it as domain 1, right? Next slide. But if I use the same model or same sentiment classifier to categorize sentiments in healthcare domain, right? So it may not work pretty well on the healthcare domain. Though it seems intuitive, like sentiment categorization is a very general problem. Like there may be some polar words in one domain, good, or there are universal polar words which hold true in all the domains. But I'll show in later slides, like there are ways, like people generally tend to express sentiments differently in different domains, right? And these features may not be common across different domains. I may talk about a telephone product in a very different way than a healthcare product, right? So a model trained on sentiment categorization for telecom product may not work pretty well for a healthcare product, right? So that's the major challenge in machine learning algorithms. And how people generally solve this is, okay, now you have a data in healthcare. What you'll do is you'll again hire some experts or humans to annotate the data for you in healthcare domain so that you can train a model specifically for healthcare data and then do the same sentiment categorization. So this model is not scalable. You can assume like there can be different domains, healthcare, retail, finance, and so on. So it's not a possible solution to again retrain models. Next slide, please. So if we take a step back and analyze why it's a problem with machine learning algorithms, what is the fundamental assumption they work on which leads to such kinds of complication, right? So this block here shows a traditional flow of machine learning algorithms, how to work. So they have a training data, right? You have some kind of training data on which you train your model, right? And then you have testing data on which you apply your model, right? But the basic assumption behind most of the machine learning algorithm is that the training and the test data follow similar distribution, or they are coming from the same distribution, or they have same feature space, right? But in real life application, for example, just take the example for sentiment categorization from telecom to financial domain, right? The use of terminology may be very different from in telecom to healthcare, which makes this assumption does not hold true in the real life setting in that example, right? So that's the case where machine learning algorithms fail. So I just showed that like the training data you want to classify some squares, red squares, and the test data is like classifying green triangles, right? So the task is same. Let's say it's a two-class classification, but the data may differ, right? It may differ in terms of features. For example, let's say when you were classifying English web pages, your features were in English language, but now you want to classify Chinese web pages. So now the feature space has changed, right? So a classifier or a model trained for classifying English web pages won't work for classifying the Chinese web pages, whether I want to do the same task to classify it as positive or negative web page, right? Okay. Yeah. So this limitation leads to a very non-practical scenario where for every domain you have to independently train your machine learning models, right? Which is not feasible. So that's the problem which transfer learning or domain adaptation attempts to solve, right? So what we do is we want to reuse the knowledge or adapt our solutions or adapt our models which are already trained for telecom domain to work well for the healthcare domain with minimum supervision or minimum need for labeled data in the new domain, right? So what we want to do is, let's say we have a model trained on domain A, which was telecom domain. Let's take the same example for sentiment categorization. So what I learned from this domain A is some kind of knowledge, a knowledge to classify text as positive or negative, right? Which may not be same in or in terms of feature space or in terms of distribution to the domain B, but still I have got some idea how do I classify a text as positive and negative, which I call as knowledge. So now instead of, when I see a new domain, let's say domain B, instead of following the traditional ML approach of manually annotating data and training a model independently, what I do is I want to reuse this knowledge and adapt my models, which I have already learned in domain A, to work well on domain B with minimum supervision. Most of the times we are able to do that without using any label data from the domain B, but you may also want to explore the scenarios where you use some kind of label data from domain B. So this is the gist of transfer learning or domain adaptation, what these techniques are. So their main focus is to make your solutions or existing techniques reusable or adaptable to a new domain, so that you don't have to retrain your models from scratch on expensive or time consuming, by using expensive and time consuming human annotations, right? Yep. So this transfer learning is not a new concept. It has been there in literature for around a decade now. And if you intuitively see, it's not new thing. Like as machine learning goes towards imitating human behavior, this is something like you can see a child, he always tries to learn from his past experience. Whatever knowledge he has in other tasks, he tends to reuse in other domain. So this is again an attempt to mimic how humans transfer their knowledge, right? And there has been different settings where transfer learning can be useful and how it can be done, right? So similarly, taking an example, like if you know C++, transforming to Java is easy. If you know maths and physics, then learning the concepts of computer science becomes an easier task for you, right? So in transfer learning in machine learning community is again to provide an ability to algorithms to adapt to a new scenario without requiring lots of label data, like. So I talk about domains and tasks here. So what a domain, so we'll use this term quite loosely, sorry for that. But a domain can be a set of entities, like for example, it can be some text documents from telecom, some text document from healthcare. And task would be, let's say in this case, it's a 2-class classification, sentiment classification task. But there can be different tasks like 3-class classification or a sequential labeling task where you want to try to annotate conversations or any other task, right? And this has been a very hot topic these days. Like you can see a lot of tutorials and workshops on transfer learning, domain adaptation in top tier conferences, and lots of emphasis because as machine learning algorithms become widespread in our daily life and are used in all scenarios, it's very important to make sure that how we can quickly and efficiently train those models without lots of input from humans, and to make those systems in terms of an autonomous in some sense, right? Okay, so I already covered this one. Yep. So let me go over an example which will make it further clear how, when I talk about different domains and different tasks, what do I actually mean. So let's take a simple example of sentiment classification again. So I want to do a sentiment classification. So, and these are all my 4 domains. Let's say books. So let's say these are some reviews on Amazon. There were some reviews about books. There were some reviews about DVDs, kitchen appliances, and electronics, right? And like for many companies, sentiment analysis on this social media data is a very crucial task to know how people are talking about their products and brands and what is the reputation and if they want to change some of the policies and all. So sentiment classification on this huge amount of user generated content on social media is one of the important tasks. Let's say one example here is categorizing these reviews as positive and negative. So let's say these 4 are my 4 domains, and I again want to classify some of the reviews as positive and negative, right? So a traditional machine learning algorithms, what it will do is, like let's say domain A, I have some reviews which someone has marked as positive and negative. I will train my sentiment classification and will apply it on new incoming data or on books domain itself. And if I do that, I could get a pretty good performance out of around 87, 88%, right? Because it's the in-domain performance. I am training my model on books domain, and also testing it on books domain, right? But what if I have now a sentiment classifier trained on some other domain, let's say domain B, and now I apply this classifier on domain A. So the data in training and tests are quite different. So I see that there's a lot of drop in performance. It drops down to around 71%, right? And if I go back and see what was the cause, like because I was doing the same task sentiment classification, why it happened. So if I see here, so there are some features or some words which make these reviews quite different. Like as a human being, people tend to express their sentiments in a very different forms for two different domains. For example, in electronics domain, compact, easy to operate, very good picture quality, look sharp. These can be positive things for me, right? And for a negative content, it would be also quite blurry in dark settings. I will never buy an, sorry, HP again. The game is so boring. It's in a video game settings. Can be a negative thing, but it was very realistic shooting action, hot, good. I was hooked up to these games. So you can see, like in electronics and video games domain, I use very different words for expressing my sentiment, right? So when I train a model on electronics, so it gives more weights to these words which express sentiments, right? Which are not at all present in my video game domains, right? So when I apply that model on that video game domain, it gives a very bad performance. Again, some examples in NLP can be like spam detection, right? For example, in an organization, you have different criteria for what emails or messages you mark as spam or not spam, right? For example, if I, as a foodie guy, interested in hotels and restaurants, so whatever mails comes which have some promotions for restaurants or hotels is very interesting for me, right? But if my colleague is not interested in foods, she is interested in some plays or movies, and those kinds of emails may be very interesting for her. So how do we and it may be very difficult for us to train a independent spam detection for every employee in a company, right? For example, let's say there are thousands of employees. I can't train a spam detection, 1,000 spam detection which works independently on each of you, right? And it may be very difficult for me to get data for to train an individual classifier for each of you, right? So what we can do is, how domain adaptation has been worked here is, we train a general model for all the employees. Like there may be some things which are always spam for most of us, and then there's a small stage which adapts to individual users, which you can call as personalization, right? So you don't have to train a model for every individual, but what you can do is you can train a general model which on an overall picture detects what could be a spam, and then based on your behavior, what kind of emails you think are spam, it adapts to yourself, right? Or it becomes personalized without requiring a lot of data from every individual, right? And again, some of the examples are in part of speech tagging in NLP, how part of speech tags changes from a news corpus to a medical corpus and all those stuffs. So just to tell you about how these settings may vary. So let's say green is the source domain and red is the target domain. So you can see them as training and the test data. And there can be two variations that may lead to a drop in performance, right? One variation could be like a domain can be expressed as access is, let's say, the feature space. What is the feature? For example, it may be documents in English versus documents in Chinese, right? So the feature space is changing now. So when such thing happens, a classifier trained on one domain may not perform well on the other domain. Similarly, when the distribution changes, like for example, distribution may be, there are two web pages which are written in English, but one talks about politics and the other talks about sports, right? So the feature space is same, they are talking in English vocabulary, but the distribution of words, how they use to emphasize politics versus sports may be different. So in such scenarios also, we may require domain adaptation or transfer learning settings, right? Next slide, please. Okay. So the other case where transfer learnings or domain adaptation settings would be required could be when my task is changing, right? You have a question? So how tasks may differ, right? For example, I had, let's say the review classification problem. So these reviews were initially marked with 0 to 5 rating, right? So now my task may change whether I was talking about sentiment classification as positive versus negative. Now I may want to do a sentiment classification as a 3-class problem, positive, negative and neutral. So do I need to retrain my whole model again for this 3-class problem? Or can I use some of my knowledge that I learned in 2-class problem while solving the 2-class to quickly adapt to a 3-class classification problem, right? So that's how my task changes. And the other way could be the conditional probability changes, right? For example, taking the review example, let's say all my reviews on Amazon were marked with a rating from 0 to 5, 5 being the positive one and 0 being the negative one, right? So now initially one of my tasks was all the reviews which were marked more than 3, I consider them as positive, and all the reviews that were marked below 2 were negative for me, right? But now the distribution has changed. Someone asked me to relax the criteria and they say that all the reviews which are marked greater than 4 are positive for me, and all the reviews which were marked as 3 or below are negative for me, right? So now the distribution has changed. The task still is 2-class classification problem, but my decision function has changed. So in this case also, your traditional machine learning algorithms won't work, and you would need some kind of adaptation or transfer that you can quickly or efficiently adapt your models to these new tasks. Either it's a change in distribution, either it's change in feature space, either it's change in tasks or the distribution of the tasks, right? So if you have any questions, yeah, sure.
Really classify, like train the classifier again, right? So does that really fall in the, like, should you really call that as a domain adaptation? Because the feature space is changing and you just have to transform the feature, not learn again.
Yeah, so transforming feature is again like you, so this is called as an heterogeneous transfer learning scenario where your feature space are completely different, right? So there are some words from English to Chinese, so this is called an heterogeneous transfer learning. One of the solutions could be where you transform both the features to an intermediate level where the difference between English and Chinese language is minimized, right? And you train a model on that representation such that it holds good for English as well as Chinese representation, right? So in that sense, you are bridging the gap between the two feature spaces which are in English and Chinese language. So that's also a kind of heterogeneous transfer learning that you would like to use. Because let's say in Chinese you don't have labeled data, right? You just have some features, but you have labeled data in English, right? So you may want to use that common feature space to bridge the gap and transfer the knowledge from labeled information in the English domain to do the same task in the Chinese
So
right?
that's what I was trying to say, that you will extract features such that that is independent of this space, right? So you really don't need to learn again, or like the distribution is not changing.
Yeah, distribution is not changing, but the feature itself has changed a lot, right? Let's say, and you don't have any label data in the Chinese language, right? So
Yeah.
how do you want to learn a classifier in Chinese when you don't have label data, right? That you can only learn in English language, right?
Yeah, then you
and
will
if
transform. You may translate the Chinese to English.
yeah, but
different sentiment will be forming a cluster somewhere else. So both will have a different distribution, and by that we can train our classifier. We did not change our domain from one particular domain to other. So just by transforming the feature space to a intermediate domain and learning some salient features out of it, so we can do that. So why do we, is there any other benefit that we learn through domain adaptation?
sorry, yeah, you please.
Yeah, so actually transfer learning is a huge machine learning field, and although we use the words domain adaptation and transfer learning interchangeably, but domain adaptation is actually a specific part of the transfer learning paradigm. So in transfer learning, I absolutely agree with what you all are saying, that to transform the features into a common subspace and then to learn on them. So actually a subset of the transfer learning mechanisms which are called featured transfers. They deal with exactly these problems, that if you have say something on some language A and you want to transfer it to some language B, so in this non-homogeneous setting, how do you learn the common features that are shared across the task? And another very practical issue is that, for say if I have 2 or 3 Chinese texts, I can translate them to English and then I can classify them, assuming that I have a perfect classifier. But say I have a post tagger for Chinese and I want to build a post tagger for English, or vice versa, then how do I learn the post tagger for the Chinese language as it is? I am not going to change it to the English language. Or if I have some document classified in English language, I want to classify document on Chinese language only. So yeah, so it is not a very, it does not comes within the very accurate definition of domain adaptation, but it is part of the whole transfer learning paradigm. Thank you.
Any other question? So maybe I'll hand over to Manjeera to go over some of the techniques in domain adaptation and transfer learning.
This red one, right? Red one?
Yep.
Yeah. Can I have it? Yeah. So as I have said that transfer learning is a very huge and diverse field. So there are always some questions associated when we are transferring knowledge from one domain to some other domain. So the 3 basic fundamental questions are, like, which are the things that we need to transfer, because there are some part of the transfer learning, although it seems very convenient, but sometimes it may actually occur that when we transfer knowledge from a source domain to a target domain, my performance decreases, which is said as the negative transfer. So like when to transfer and when to stop, this is a very important question whenever we are dealing with some transfer learning application. And the second thing is how. Just now I have said that there are many kind of approaches, I will come into that, and many kind of mechanisms through which actually I can reuse and adapt my knowledge that has been learned on the source domain. And the third point, which is related to the first one, that when to transfer, when I can actually get benefited from transferring. So, the transfer learning, they have 2 main components. First one is the domains and the second one is the task. So, whether my 2 domains, the source domain and the target domain, they are same or different, or my tasks are the same, based on that we categorize transfer learning on 3 groups. The first one is the inductive transfer learning, in which the domains are the same, but my tasks are different. So it is called inductive transfer learning because as my 2 tasks are different, that's why I need some target data, some label target domain data to induce my classifier or my predictive function. And the third point I will go first, that is the transductive transfer learning. So actually the domain adaptation as we understand it, so this comes within the transductive transfer learning part, where my domains are different. Say I want to adapt a document classifier from a retail domain to a financial domain, but my classifications are same. Say I want to classify them based on a binary sentiment classifier. And the third group is unsupervised transfer learning, which is the hardest of all, because here I have 2 different domains and 2 different tasks as well. So in that case, generally those algorithms which deals with clusterings, they comes into that unsupervised transfer learning umbrella. Yeah. So from transfer learning, we can actually go to two direction. First one is a homogeneous transfer learning, and the other one is the heterogeneous part. So The homogeneous part is that whenever, suppose we have some task in English language and we want to adapt to some other task in English language only. So that's why like my underlying main linguistics features are same. And the other heterogeneous component is that, as the example of English and Chinese, where on my linguistic components, they differs very much from each other. So it is entirely a new feature space that I have to move on to. And all these two things, they have these three components as well, that supervised, semi-supervised and unsupervised. So these are nothing but the same machine learning concepts of whether we have some target domain level data and how much level data do we have, or all, or we, yeah. Yes, so hetero and homo is just, I have said, suppose when your underlying features are not changing to a very drastic dimension. Suppose in a domain adaptation, say I have a document classifier for say 5 topics in English language, but in some domain A. And then I will want to move into domain B in English language documents only, but now I have to reuse or adapt the knowledge of my classifier into domain B, because I cannot use as it is. Yes? Yeah. No, the domains are different. Suppose the example of say finance and retail. So the domains are different, or different kind of blogs, say on suppose on politics and on science. But their underlying, they share the kind of same linguistic features that we have. I have to. So there are some heterogeneous transfer learning work that goes on in the image recognition community. Yeah, if you want to.
For example, it can be like you have some classifier or models on text, right? And now you want to do some kind of same thing on images, right? So the feature space are completely different. Text, you have different feature space, and for images you have different feature space, right? So when you are adapting your model from image space to a text space, so the features are different, so that's why that comes in a heterogeneous transfer learning setting. While the homogeneous transfer learning setting, the feature space are essentially the same, right? So for example, in a web page, you may have images as well as text, right? And using some of your knowledge about the text that is written on the web page, you want to do something, you want to classify the images that are also present on that web page, right? But when you process those, the features on which you represent images and the features on which you represent the text that is present on the web page are different, right? So when you want to do a transfer or adaptation from a domain to another domain where the features are very different, that comes in heterogeneous feature space, right? And homogeneous would be like the features are same, like it can be English to English or text to text, right?
Okay.
I just wanted to ask that for image and text, the feature will be very different. Like, can you really like get a have you seen getting a good result?
For English too?
For text and images, the features will be very different,
Yes.
right? So like the feature space, the dimension, everything will differ. So have you really seen any real life scene where you are getting better result when you are doing a transfer learning from text
Yes,
image?
the example which I gave you, like you
Yeah.
have web pages where you have images as well as text, right? But you don't have any labeled data about the images that are present there, and but you only have some kind of labeled data in terms of the text that is available on the web page.
Yeah,
right?
it works good.
So it works good. In the same case, like you can follow your idea of Chinese to English as well, like where you want to learn some kind of intermediate representation, right? So again, when in the web pages where you have images as well as text, you may want to learn some of the features which may act as a bridge between the image space and the text space, right? And then work on that bridge that you have got, right? That can be your intermediate representation where you can push knowledge from that you have learned from text to the image space, right? So that's just an intuitive overall idea, like how you would address a English versus Chinese problem as well as a text versus image space representation problem. So both of them falls in a heterogeneous transfer learning scenario.
Yeah, I think image and text is a bit difficult, right?
Yeah, that's difficult, right? Even heterogeneous, all English to Chinese is also different. Like we are talking about, like you can just translate all the page, but that does
Yeah,
not
that is
work
not a
in real life.
solution,
Like
yeah.
that's also a challenging problem in itself.
So like,
Just in continuation to her question, so these days we have videos wherein there is no label, but then when you are seeing the videos, you can build in a classifier who just narrates the video for you, as in text. We have this in semi-supervised learning.
So do you have the transcripts with the video as well?
Yes, like there is no label for it, but there is a scene that is going on, supposing a birthday party, so that the salient features and everything, they're extracting the salient features because supposing for the example of a birthday party, so there will be colors, there will be a cake and something like that. So they're extracting actually the meaning out of a scene and then they're narrating the scene to you. So as you were telling that both the spaces are different, but then they take out the salient features from the images, and then with that they're correlating the text space, and then they're narrating the scene for you. So that is, I guess, is possible.
actually, just to add to that, actually, these kind of things, they are part of this multimedia analytics
right,
thing,
exactly.
in which the whole framework works like this. You first do the video analysis. These are
Yes.
called the actor and action identification.
Right.
Then you, from that video and image features, you try to understand what
What is
all
the
can
scene?
be present on the scene. Then you actually use a natural language generator or understanding kind of system to first get a very basic text representation from that, and then actually through improvisation, if you want to build say very concrete human understandable text, then you do on that. They can improve on that part. So I am not sure how much of transfer learning they use on that thing, but that things definitely comes on something like, it is not you are using the video knowledge to learn that text classification. It more like you are learning the video by itself, and then you are mapping to some object properties, and then you are getting your natural language output from that.
Is it? Okay, like in one of the papers I've seen that they were doing it simultaneously, like they were extracting the
Yes.
so they were extracting the videos and they were learning it online, that there is
Yes,
no offline
Yes, absolutely. So whenever you are extracting the video, the idea is to learn from whatever is present on the current frame, and then you are actually mapping them to your natural language understanding unit
whatever corpus I
or to
have.
your knowledge base. Yeah. Thank you. So I will be quick, only 10 minutes left. So actually now through all these inductive, transductive, unsupervised, they are the broad umbrella categories. So now inside each one of them, we use different kind of mechanism at the data level to actually do the transfer of knowledge. So in the instance-based approaches, I will start with that because it is the most intuitive thing. What we assume is that some of my source domain label data that I have, I can adapt them as it is. I just need to reweight them so that they can fit to the target domain. And in the process of reweighting, I also eliminate the label source data that will be not helpful for my target domain. This is done with like something can be very simple to implement, like a source and target domain binary classifier, and then just reweight those instances. So it uses the same logic as AdaBoost. What it does is that to get from a weak classifier to learn a strong classifier, in that case, as it is a transfer learning, we push the error towards the target domain data. And then comes second, the feature-based approaches. So feature-based approaches is again the same thing, that if you have seen different languages, the features are entirely different. How can you learn some shared features? Even for the homogeneous transfer learning part, the feature representation, there are some tasks. In that cases, you cannot just use the whole instance as it is. You need to reweight the individual features that are represented. And in the relational based approaches, it is it is a kind of logical transferring that we do. Say I have, can you give next slide please? Next. Next, next, next. Next, next. Yeah. So suppose I have some academic domain. Now consider these relations. Like say, a teacher advise a student and a paper is produced. And same, now we can transfer these relations, these logic or the mappings to a movie domain. When a director is, they advised an actor and the film is produced. So this kind of relational mapping is considered in the relational transfer learning. And the last one is the parameter based transfer learning, which is say, I will explain it with just a simple classifier example. Suppose I have trained the source a source domain SVM classifier or any kind of the classifier. So with each classifier I get an weight function. So now I say that I will adapt the classifier to the target domain. But I don't want to reweight the features or the instances. So, but I want to change in my weight function itself. So I try to segregate which part of the weight function they are common across the two different domains, and I also segregate the source domain specific weight function, so that in target domain I only have to learn my target domain specific counterpart of this weight function. And just to an example of negative transfer with all the advantages of transfer learning, but there are some points where we actually get poor performance if we use transfer learning. So this field is still being explored by the academia to understand when to stop and how much to transfer. Just a small case study. So we did a transfer learning example in the for the conversational database. Say we have some the conversation present in the telecom domain. Can you press next? Yeah. And we apply that to the same the conversation labeling on the same domain. Next, next. Yeah. Next. So when we, yeah. So now we try to again label the conversation on the finance domain without getting new set of annotated data, because that will improve our the readiness to classify the conversation data. So, but we get a significant drop in performance because we haven't performed any kind of adaptation. Next. Next, just complete this slide. Yeah. So for this specific task, what we did is that we took two-stage domain adaptation technique. We actually employed both instance-based approaches and feature-based approaches. Next slide, please. Next slide. Next. Next. Yeah. So in the instance-based approaches, what we do is that we take this similar instances from source and target domain data, which comes within this intersection area, and we just reweight them to get a good adaptation. And in the feature-based adaptation case, next slide. Yeah, we actually learn the generalization on the feature representations from the source and target domain data. Next slide. Next, just play, yeah. Next, once again, yeah, thank you. So as you can see that even with zero target domain data, with using this two-stage domain adaptation approach, we have got significant improvement in our performance. So, and next slide, this one is the next, yeah. So just to give you the knowledge that in Xerox we are trying to give this domain adaptation or transfer learning functionality as a web-based service where You don't need to train your own domain adaptation model every time. You can upload your data and you can just get the the new adapted model to train on the training data. So I will conclude with that. Thank you. Yeah. Can you just end the slide, please?
About, I kind of didn't get it very well. The feature
Yes.
adaptation. What can you please explain that once?
Yeah, Himanshu, can you actually say what you did in
Sorry?
the feature
The feature
adaptation?
adaptation
in
which she explained on the slide, I couldn't
Yeah,
get
so
that.
feature adaptation, let's say when I gave an example of some electronics to video games, right? I showed there were some features which were completely missing from electronics domain and were present in video games domain and vice versa, right? But there, if you see intuitively, there could be some features which are present in both domains. For example, if it is a task of sentiment analysis, good, bad, these are some universal polar words which may be present when I am representing or talking good things about electronics or good things about the video games itself, right? So in a feature representation, a simplest approach to bridge the gap between different feature representation could be, I want to find the correlation of how some words which are used specifically in electronics domain to represent positive sentiment, how they correlate, how they co-occur with a universal polar feature, say good. Let's consider good and bad are my pivot features, right? So these are the features which occur in both the domains, right? But they are not sufficient to just train a sentiment classifier. I need to learn some domain specific features, right? How do people talk good things about electronics, or how do people talk good things about video games, right? So like these good, excellent, these can act as my pivot features. So pivot features are, these features occur in both the domains, right? So now what can I do simply is to find the co-occurrence, how that domain specific word, let's say the game was very engaging, right? How, so that could be co-occurring with a pivot feature, let's say good, right? So I know if that domain specific feature in video game co-occur many times with good and some other features in electronics domain co-occur many times with good, then I intuitively learn a relation that the domain specific feature in electronics and the domain specific features in video game domain that co-occur with good share the same relationship in two different domains, right? Similarly, I can do for some words which have same kind of correlation with negative words, let's say bad, worse, right? So now I can learn a kind of mapping how some words in electronics domain, which are very specific to electronics domain, are very discriminative and polar, how they, what could be their parallel word in a new domain, right? So this is a simple example of how do I bridge the feature gap between electronics and source domain. So now once whatever weights I learn through a model for those domain specific words, I can directly transfer those weights to the words which have the similar relations or have similar sense with good in the other domain, right? And I can use simply transfer those weights. So this is a simplest technique that you can do, and it has been widely used for specifically for sentiment analysis, and this technique is known as structural correspondence learning, where you want to learn the correspondence between how those words occur in two domains, right?
Yeah, but okay.
Sure, maybe.
Yes.
Comments with some other.
Yeah, that's a very good comment. Yeah. So in this, we haven't presented the work here, but yes, that is very important to see, because while expressing sentiment, people can be sarcastic. Like for example, if I am a fan, I love horror movies, then I can say like a scary movie can be a very good thing for me. Like, but in another domain, a scary holiday destination can be a bad thing, right? So in this case, your SCL-based approaches which find correspondence between good or bad won't work, right? So this is very important thing, and we are also working on. So we call them as constant polarity words or constant changing polarity words. So yeah, this is a very interesting line of work we are pursuing. Maybe we can talk offline to discuss how we are working. But that's a very important problem, right? Like because some words maybe can be positive in one domain and can be negative in other domain. For example, the scary example I gave you, right? And it's a very important problem to address such words in a sentiment classification specific problem. Oh, thank you very much.
Thanks a lot.
Thank you.